So good morning everyone. Today I'm going to talk a little about video compression with the MPEG-4 standard. My name is Nadhirah Badrulkamal and I made this slide with my dear friend Kinanti, Wening, Asih. So let's just talk about today's topic. So what we're going to talk about in this video is first the introduction, second is the definition of MPEG, dive into MPEG-4 standard, basics of video compressions, types of predictions or frames, closing loop encoding, and motion composition. So first, the introduction. Today's topic is video compression methods, specifically the MPEG-4 standards. Now first, let's learn about MPEG standards itself. So it is a standard developed by the International Standardization Organization, or ISO, for the compression and transmission of the audio and video data. They are designed to make it easier to have efficient storage and transmission of digital multimedia content. Essentially, it helps you store and send multimedia data, like for example videos, more efficiently. You can really see how this helps in a lot of things like video sharing and streaming. So MPEG has a really long history, dating back to 1992 when the first one, MPEG-1, was created. And the next one is MPEG-2, made in 1995, and then MPEG-4 is made in 1999, and the last one is MP4, which is widely used today and is made in 2003. So there are three key features of MPEG-4. The first one is versatility. Versatility is it means that MPEG-4 supports a wide range of multimedia applications. And then we have compression efficiency. Compression efficiency means that it has efficient compression algorithm with high quality results. And the last one is object-based coding. So object-based coding means it allows encoding of individual objects within a scene, enabling more flexible content manipulation. Next, we see that MPEG is actually used in a lot of things. In multimedia, MPEG is often used for streaming, video conference, telecommunication, and digital television broadcasting. While for interactive application, it is often used for virtual reality and augmented reality experiences, and also multimedia gaming and simulations. So to recap, there are benefits and challenges in using MPEG standards. The first one we're gonna talk about the benefits we'll get. So first is high compression efficiency. So using MPEG enables you to store and transmit multimedia content with reduced file size while still maintaining their quality. Second one is versatile multimedia support. Means it supports a broad range of multimedia applications. And then the last one is interactivity and object-based coding. So it permits the encoding of individual elements in a scene, making it more flexible and increase user engagement. There are also challenges in using this standard. The first one is patent licensing issues, because it will complicate the adoption and the use of the standard due to legal considerations and associated costs. And then the next one is the expanding technological landscape. So MPEG needs to continuously adapt to stay relevant to the market. As we can see that there are multiple versions of MPEG, such as MPEG-1, MPEG-2, MPEG-4, and etc. And knowing this, MPEG standards must always evolve, and continuously adapt to whatever changes in the technological landscape. So now, moving on to the next topic. We think about this for a second. 1 minute of 24 FPS 180p video usually contains about 144 frames, 2.9 billion pixels, and about 71.7 gigabytes of data. And that's really a lot of data. So how do we send that huge amount of data? Well, the answer is video compression. So what is video compression? What is the general idea of it? It's very where we encode and restructure data of a video in order to reduce its size. How the video looks before and after the compression should be the same. And this is very useful when you need to send huge amounts of data in form of a video in a fast way. So for example, streaming, where you need to send live video feed in a very fast speed. So to learn more about video compression, we have to learn more about codec. Codec stands for coder and decoder. And it'll take the original file that has a huge size and then put it through an encoder. And this encoder will result in a smaller file size that is easier to store and to transmit. And if we want to watch the video again, we can put it through a decoder, and the file size that we are watching will be smaller than the size of the file that we put in the encoder. Then we learned that there are two types of video compression. The first one is interframe compression, and then the second one is intraframe compression. So the first one we'll talk about is intraframe compression. Intraframe compression, or is also known as spatial compression, is the process of compressing a video by compressing the images of every single frame. So as we can see here, each frame of the video is basically a picture. It's an image, and we compress each frame of the video to a smaller size, and it'll help to reduce the file size. It'll help to reduce the file size, but it still stores every frame in the video. So it's not the most optimal way to store and to compress a video, which is why we go into the next type of compression, which is the interframe compression. So interframe compression, or it's also known as temporal compression, is the process of compressing a video by removing redundancies within the frames of the video. So to understand this, we have to know that between each frames, there are differences between the frame right now and the next frame. And what interframe compression is doing is that instead of storing every single frame with all the redundancies, because sometimes a frame doesn't really look that different from each other, it stores everything different between the current frame and the next frame. And we'll learn about this later, where we dive deeper into how interframe compression works. So the next one we'll talk about the types of prediction. There are three types of frames within a compressed video. First is the intraframe frame, second one is the predictive frame, and the third one is the bidirectional frame. First is the I-frame. The I-frame, or the intra-coded pictures or intra-frame frames, are complete images that does not have a reference to the previous frame. So picture it as a full-on JPEG or PNG picture. It stores a whole image and it does not have a reference to any other image. It's a whole fully completed image that the video stores. And this usually serves as a reference point for other frames. And the next one, we have the P-frame. The P-frame, or the predictive frame, only holds the changes from the previous frame. So remember that we have an I-frame. So the P-frame only stores the difference between the previous frame, which can be an I-frame or another P-frame, and the next frame. So for example, we have this reference frame right here, and the P-frame here should only contain the data that the cat's hand is moving down. Of course, it doesn't really store it in text, but this is just for this video alone. So it only stores the data that the cat's hand is moving down, and the results is, when the video is all put together, will be that the cat's hand is moving down. The next one is B-frame. B-frame, or bidirectional frame, keeps the changes from two different frames, the previous frame and the next frame. So the reference frame for the B frame can be an I frame or a P frame. So for example, this is a B frame. The B frame has two references, the previous one and the next one, and it calculates the difference between frame 1 and frame 2. And this difference will be stored in the B frame. The difference between the P frame and the B frame is that the P frame only stores only reference one frame. It only reference one frame, and it only stores the changes it has between that frame and what's coming next. But it does not reference the next frame. But B frame needs two different frames in order to be made. Now, we have to remember that B frames also create a difference between display order and transmission order. So for this example, we can see that there's three frames here. First one is intra-frame frame, the second one is the bidirectional frame, and the third one is the predictive frame. So the first one will be get transmitted first, and then the next one, instead of the B frame, we actually need to transmit the P frame first. Why? Because the B frame has two different dependencies, the forward dependencies and the backward dependencies. And we cannot display this frame without knowing what the next frame is going to be. So the display order here is actually I1, B2, and P3, but the transmission order is actually I1, P3, and P2. Now these arrows actually visualize the forward or backward dependencies of the frames. Next, we learn about closed loop encoding. So what is a closed loop encoding? So closed loop encoding is like having a smart video encoder that receives a feedback on the quality of the compressed video it produces. So you can picture it like an encoder that continuously receiving feedback about the quality of the video it produces. It then constantly improves and tweaks the encoding parameters it has, so you'll get the best quality that it can give. And because it continuously gets the feedback, it will always continuously find a way to optimize itself, leading to better quality results and more efficient work. Next, we learn about what can it do based on the feedback it receives. So it can do a lot of things. First is adjusting the bitrate, and then adjusting the quantization, and then strike a balance between efficiency and quality, and the last one is to continue involve the encoding strategy. So what is the ultimate goal of closed loop encoding? So the ultimate goal of closed loop encoding is consistent video quality. Why? Because it will try to continuously tweak and improve to make sure that you'll be able to get a consistent video quality. So here's a diagram that represents how MPEG-4 closed loop encoding works. It starts from the disk, and this serves as our input, and it'll end in this output, which is the compressed video. And the stream then assumes that a master video represented by an MPEG bitstream will set the standard for key parameters like picture size and structure, and with this, the system can efficiently edit and manipulate videos without fully decompressing and recompressing them. Now, we'll learn about three key aspects in a closed loop encoding. So we have masters, we have slaves, and we have JPEGs. So masters is the primary or original video source, and it serves as a reference. And it is usually represented by an MPEG bitstream, and it contains various compressed data. It also sets a benchmark for various parameters of the video. And then we have slaves. Slaves are additional video sources or streams that undergo encoding based on the same parameters that is established by the master. And maybe they are secondary videos that is encoded with the same specifications as the master, and their goal is to maintain consistency in encoding parameters and quality across the slaves and the masters. The last one is the JPEGs. So JPEGs, this here is it represents the JPEG compression that is being used for certain functionalities within the closed-loop encoding system. Specifically, it mentions get JPEG header and get picture functionalities. Next one, we'll learn more deeply about the masters. So, masters, the master video is processed sequentially, and we can retrieve the GOP header with the get SEK header and get GOP header functionalities. And then we can retrieve the picture header data with the get picture header functionality. And then we can retrieve the compressed frame content with the get picture functionality. The put functionalities here then modify the headers back into the output bitstream, and it ensures consistency with the master's video structures. So this streamlined process allows more efficient encoding, all while maintaining the essential video parameters. Next is the slave. So slave videos also went on sequential processing loop. We can retrieve crucial information about the sequence and the GOP structure by using the get SEQ header and the get GOP header functionalities. And for the slaves, there might not be a direct put step, and instead the loop may return to the initial steps after get picture header. Next, we'll talk about get pic. So this functionality obtains the picture's information, which is the syntax detail and the DCT block data from the video stream. And then we can align and adjust the frames by using the frame alignment functionality. And this CVRE is a specialized engine designed for detailed editing operations on compressed video streams. Now, next, everything that we get from the previous process is then combined into a final output, which is the compressed video. Now, we already talked about closed-loop encoding. Next, we'll learn about motion compensation. So, in a typical video of the a lot of the consecutive frames are similar to each other. And storing all of the frames will make us store a lot of redundancies. So instead of storing every single frames, why don't we just save the differences between each frame? So for this, we will learn a method called motion compensation. So how motion compensation works is that, so you know how in a video some parts of the frames move and some don't? We can actually track these differences between the frames by tracking where they go in each frame. And we can have this reference frame. And for the next frame, we can assign a motion factor for where that object moved in the next frame. Now, example here is using block motion compensation, where you divide the frames into 16 by 16 macro blocks. And the disadvantage of this method is that it does result in discontinuities at the block borders. But as you can see, it tracks blocks for the motion compensation. Next, we have to learn about block motion estimation. So block motion estimation means instead of checking if each block in the frame has changed or not, we can track where the block is in the next frame. So for example, this is the reference frame, and this is the block we are tracking. So in the next frame, you know that the block moved here. That's the data that we store. We only store that this block right here moved right here, and this method is called block motion estimation. However, motion compensation alone is not enough because it is not enough data to recreate a video to the quality that we wanted. So we have to learn about residual frames. So what is residual frames? Residual frames is basically when you have the current frame and you motion compensate it, and then this result from the motion compensation, we basically measure the difference between the motion compensated frames and the next frame, and it'll give us the residual frames. And we store these residual frames because it has less information and is highly compressible. Why? Because we need it in the decoding process. So motion compensation is not enough to give us the quality that we wanted for our video. So for this, we use the residual frames, and we first have the current frame, we put it through motion compensation, and then we add the residual frames that we got from the encoding process to create the next frame. So that's all for this topic. I hope what I explained here is genuinely helpful, and this video was made as a final project for my multimedia systems class. So I hope I did well. Thank you very much.